Okay, this is going to be the lesson for AP Statistics, Chapter 12, which is on sampling techniques and biases. So following the notes here, let me present those. Okay, so in Chapter 11, we talked about how we can simulate collecting data by not actually collecting real data from the world, but by using randomness and some sort of a model that connects random outcomes to specific events in a scenario so that we can simulate collecting data, simulate conducting trials over and over again to collect data. And we do that whenever the data is difficult to collect, expensive to collect, or maybe it's unethical to collect in some way. But we have some information about the environment that we can use to model things. But the truth is, most of the time we don't simulate a data set. Usually we actually collect the data. And what we're trying to do is to figure out, in a population, how could I collect a representative sample of the data that I'm after so I can analyze the sample? And then in second semester, we're going to learn how you can then take that information and infer things about the population from which it's sampled. We'll talk in Chapter 12 about methods of sampling and the various biases that can result. So a lot of this chapter is about terminology and understanding the terms and how they apply. So first of all, we're talking about trying to assess some sort of a population, and we usually do that by taking a sample out of that population. All right. So some terms: population, that refers to the entire group of individuals that's under study. So for example, maybe it would be all adults in the United States of America, something like that, millions and millions of people, right? A sample is some subset of that population. Usually we can't take data from the entire population. Now, if we are able to take data from the entire population, then that's called a census. That's very expensive and difficult to accomplish. We do try to take a census of the data of all the households in the United States once every 10 years, and that's very difficult to do. But they try to count the number of people and various things about the people living in each house, right? And whenever we're dealing with a population, P, right, anything we measure about that population is called a parameter, also starts with P. And usually we use Greek letters for that, things like mu for the mean, sigma for standard deviation, things like that, okay? If we're talking about a sample, so we've taken a sample now of the population, then that's a subset that you've drawn out of the population, okay? And that means that every time we take a sample, we're going to get a little bit different results. So there's what we call natural sampling variation over here. Every time I take a sample, I get a little bit of variation. And that means that when I analyze something from a sample, there's going to be variation from sample to sample to sample, right? And that's totally natural, right? We'll talk about how we deal with that later in the course. Okay, the word poll is specifically when we're talking about taking a sample from humans, right? When we're asking data from humans, right? But whatever we measure about the sample we take, right, where it's called a parameter if we're dealing with the population, it's called a statistic when we're dealing with a sample. And we tend to use English letters when we are talking about statistics that are computed, like the mean, standard deviation, correlation coefficient. We use regular letters for that. There's another term which is used sometimes, and it's called the sampling frame. And so the idea there is, if you had a population, let's represent it this way, we'd like to take a representative sample, but if we were really only taking the sample from some subpart of the population, and then all of the members of the sample were taken out of that, then this subset over here, let me use a different color, this kind of subset of the population that you're sampling out of is called the sampling frame, right? It's just the portion of the population that could have been included in the sample. And sometimes that's everybody, and sometimes that's not everybody. It depends on the method of sampling that you use. All right. So a couple big ideas related to sampling. If you examine a sample, you can usually examine a sample instead of the entire population and still determine everything you need to know. It's usually impractical to sample the entire population. Okay, our textbook has a great example of this. I'm going to keep referring to this. Let's say that you're making a pot of vegetable soup. and you want to taste the soup to make sure that it's okay, right? I mean, one way to make sure that the population of your whole pot of soup was okay would be to eat the entire pot of soup, right? But if you did that, there'd be nothing left for the people you're cooking for, right? So you obviously wouldn't want to eat the entire pot of soup, right? It would be sufficient to just like dip a spoon in there, take a sample out of the soup, and then just taste the sample. And as long as the sample tastes good, you're reasonably confident that the whole pot of soup tastes good, right? As long as that sample, that spoonful, is representative of the whole sample, or the whole population of the soup in the pot. Right now, it is actually more difficult than it sounds to take a representative sample, right? Easy to take a sample, hard to take a representative sample. The goal in selecting the sample is to avoid the two enemies of statistical analysis: bias and variability. So we're going to talk about both of those. What is bias? What is variability? Okay, so bias is if the sample itself is not representative of the entire population. It's representative of maybe a portion of the population, but it's a portion that doesn't represent the whole population, right? And so that would be a bad thing, right? And then the other thing is, when we take a sample, we know that there's variation, right? But you want that variation from sample to sample to be as small as possible. So let's imagine that this target represented some population. The target represents the population, and we're taking a sample out of the population, okay? So a really good sample would be this one down here. Let me mark in green. This is the best sample down here. And the reason for that is because the sample we took was not much variation from sample to sample, and it's right on target. It definitely represents the target, okay? Right, so there's not very much variance from sample to sample, and there's no bias because the sample is right on target. The stuff in the sample is perfectly aligned with the population, right? But there's some things that would be less optimal, right? You might have a really small variation in samples. So whatever you're doing to take your sample results in very little difference from sample to sample if you took multiple samples, but it's off target, right? It should be here, and instead it's way over here. So that would be called a biased sample, right? It's sampling effectively, but it's not sampling the whole population. It's off target. Right? On the other hand, you might have something that's on target. It's sort of centered on the target, but there's a lot of variation from sample to sample. And we'll see how we can control variation, right? So this one's not ideal because even though it's on target, there's no bias in the sample. Yeah, there's too much variation from sample to sample, right? And the worst case would be if it's both biased and lots of variability. So this would be the worst case of all. All right, so the goal in taking a sample is to be on target, right? In other words, no bias. Your sample is representative of the whole population. And then also to sample in such a way that if you were to take multiple samples, they would all be reasonably close to each other. So there's not a lot of variability in the sample. Okay. So let's talk about bias first. So there are some specific terms that talk about different kinds of bias. Okay, so the first one is a general term just called undercoverage bias. And all that means is that some portion of the population is not able to be included in the sample. Classic example of undercoverage bias. In the 1936 presidential election, it was against Franklin Delano Roosevelt and Alf Landon. And a poll was taken that asked, who will you support for president? Right, and based on this poll, Alf Landon was projected the winner, 57% to 43%. So of course you've all heard of President Landon, right? No, not so much, right? Because FDR won in a landslide, 62 to 37%. So what happened? Well, what happened was, even though this was in 1936, the magazine that conducted this poll tended to appeal to wealthy people, and the poll was conducted by telephone. Right? But in 1936, only very wealthy households had a personal telephone in their house, right? So if you look at the population of all the people, right, there was only a portion of those people who had phones, right? And since the sampling frame was just that, when they took the sample out of just the people with phones, they completely missed all the people that didn't have phones. All these people had no ability to be included in the sample, and so therefore the sample was biased, right? So this particular kind of bias is called undercoverage bias, when we simply do not include a portion of the population to be allowed to be sampled from, okay? But there's other kinds of biases. So the next one we're going to talk about is called response bias. So a response bias is if there's anything in the survey design which influences the responses of the subjects. In other words, this is more applicable when we're talking about humans now as opposed to sampling data or some sort of measured thing. But if there's anything about the way the sample is conducted that would cause humans to change their response to the sample. So here's some examples of that. Let's say that a survey includes language which is unfamiliar to some people. They might not want to admit that they don't understand what that means, so they might make an incorrect a selection in the sample simply because they don't understand the question, right? Here's another one that's not intuitive, but possible. Let's say a survey is conducted of people face to face, and the interviewer is physically attractive. So the participant, they might want to impress the person who's asking them the questions. Maybe not even consciously, but subconsciously, they might be attracted to that person. And so they're going to try to anticipate what they think that person wants to hear. And that might cause them to change their response. If they change their response because they're attempting to, to be attractive to the people who are giving them the survey, that's called response bias. Right. The classic example is retaliation. So let's say that a participant's responses are not confidential. They might not respond honestly due to fear of retaliation. So let's say that you've got a small group of people, maybe 10 people that work for a boss, right? And then some outside entity comes in and says, I'm going to conduct a confidential survey of your employees to find out what you think, right? Well, if there's only 10 people, and all of them are honest, and it turns out that like 9 of the 10 people really don't like the boss, and 1 of them likes the boss, right? And then the surveyor reports this back to the boss. Well, the boss knows that 9 out of 10 of his employees didn't like him, and so there might be retaliation on the whole department, right? So anytime there's some sort of fear of retaliation, or there's some sort of consequence given dependent upon the answer that somebody gives, if that could cause a person to change their response, then that situation is referred to as response bias. Okay, so again, we're talking about terminology you need to be aware of and be able to classify different kinds of biases. These are the first 2 kinds: undercoverage bias and then response bias. Okay, 2 other related but different biases: voluntary response bias and non-response bias. Okay, so let's talk about voluntary response bias first. Whenever you sample people and you ask for volunteers to participate, if they have to volunteer to be in the sample, then you may get more participation from people who have more extreme points of view. Here's an example. This is a classic real example, actually. So there was a newspaper columnist. Newspapers were like sort of old paper versions of the internet, and there was a person named Ann Landers who would ask questions, write letters, and kind of have a weekly column. Well, at one point, she asked parents to write in and answer this question: if you had it to do over again, would you have children? And surprisingly, 70% of the 10,000 people who responded said no, they would not have kids again, which is usually shocking to most people because most people seem to really love their kids, right? But when they conducted a more careful verbal telephone survey, it actually showed that 90% of people are happy. Parents are happy with their decision to have people, right? The problem is if you have people who are reading the newspaper, who is it that will tend to respond to a question like that? Usually it would be somebody who has a strong point of view, and a point of view that they think doesn't get heard of enough, right? Is ignored. So somebody who's like, you know what, I don't like my kids, they're exactly the kind of person who's more likely to respond to that survey. The people who are like, oh, of course it's I love my kids, everybody loves their kids, those people probably would not call in. And so the people who volunteer to be in the sample, right, those people are often from a subgroup that's has the most extreme points of view, right? So if there's some sort of spectrum of possible answers, the people on the extremes over here and over here are the ones that are more likely to respond to something where they volunteer to be in there. Okay. Okay, a related thing is, let's say that that researchers did decide to try to use some sort of a good sampling technique to come up with a nice sample of the whole population, and they contact people. So the researchers choose a sample, but then people are allowed to decide not to participate. In other words, they can opt out. And with humans, you can't force them to do things, right? So very frequently, surveys are, you can choose to opt out. If somebody contacts you on the phone, you can choose to say, I'm sorry, I'm not interested, I don't want to give my answers, and hang up. Right. So if people just choose not to respond after they've been placed by researchers in the survey, then that's called non-response bias. They're just not responding, not providing a response. Okay. Now, a lot of people get confused between these two. So let me make this comparison, right? In voluntary response bias, the researchers do not choose the sample. The subjects are volunteering even to be in the sample. They just volunteer to be in the sample, but the researchers are not involved in trying to pick who is contacted. In non-response bias, the researchers do select the sample, but then some people who have been selected opt out. So there's a subtle difference between the two. Okay. All right, and then there's a couple of other ones that are not in our textbook, but they get mentioned, so I'm going to raise them as well. Occasionally, I've seen the phrase judgment bias come up. And so what judgment bias is if a sample is created by allowing the researchers to judge who should be in the sample, okay? So let's say that you want to collect a random sample of people who shop at the Chandler Fashion Mall, right? So if researchers go there and then they just look at the people and they go, you know what, I think that person and that person and that person and that person, that person, that person should be in the sample. Like they're picking that based on their own judgment, then that's called judgment bias, right? Here's an example of why that's a bad thing. Let's say that researchers are trying to investigate some question that has to do with religion, okay? And so they want to try to include two people from each of the religions, okay? And so who would they include? Well, maybe they would include a Catholic and a Protestant, an evangelical Protestant. They would include a Wiccan. They would include an atheist. They would include an agnostic. They would include a Hindu. They would include a Mormon. They would include the people that they know of, right? But they would include two people from every one of those groups, right? And they might completely forget, like, did you remember to include the Zoroastrians? Did you remember to include the Druids? I mean, there's a lot of different religions. So, letting researchers judge who is in there is not a good idea. And here's the other problem, right? Let's say that they build that sample so they include two of each of these types of people, right? And that means that there's two Wiccans and there's two Catholics, right? But if you look at the general population of the world, there's a lot more Catholics than there are Wiccans, right? So it wouldn't be representative to have the same number of Wiccans as Catholics, right? So, whenever you're judging things, we know that people are really bad at trying to come up with random things, right? So that's called judgment bias, if the researchers are just judging who's in there, okay? The last phrase is not really a bias in the same sense. So I hesitate to even mention it, but people mention it so much that I think I should talk about it. So you'll hear this phrase confirmation bias. Okay. Now that's not really the same thing. It's not about selecting out of a population to form a sample. Okay. What confirmation bias is about is if people are evaluating the information that they're receiving at all times, it's really based upon their current mindset, and which is based upon their previous experiences. And there are psychological reasons why humans tend to be more willing to accept things that match their existing ideas, and they're more willing to reject things that don't match their existing ideas, right? So basically what we're saying is that it takes a lot of evidence to change someone's mind, right? So when somebody is presented with evidence, right, they tend to accept more easily the things that are already close to what they believe, and they tend to reject things that are not very close to what they believe, right? So the phrase for that phenomena is called confirmation bias, but it's not bias in the same sense as these other things are. All these other things, judgment bias, non-response bias, response bias, voluntary response bias, and undercoverage bias, that has to do with selecting out of a population a sample to investigate or to research, right? This is not the same thing. So this is a different kind of bias. I'll mention it just for completeness, but it's not the same thing. All right. So how can we choose a good sample that doesn't suffer from bias, right? Well, it turns out that we need to use random processes because people are really bad at doing things that are representative or random. So most people think if you're saving people, yeah, you should select people from specific groups to make sure one of everyone is included. But we already talked about how, like with the religion example, that's not a good idea, right? In the soup analogy, it would be this. Let's say that we wanted to take a representative sample of our soup. okay, and we dip our spoon in there, right? As long as any spoonful would be equally likely to contain all the components in the soup, then we're good just with any spoonful that we grab out of that. If we, for example, let's say we just added salt to the top of the soup, or maybe we think, okay, I'm going to take a representative sample. So I know that I just added salt, so I might make sure that I stir it up so I get, some of the part that has salt and some of the part that doesn't have salt in there, right? And you want to make sure that your soup, contains, if you know that there's, like onions in it and carrots in it and potatoes in it and beef in it or whatever, you want to make sure there's a piece of each of those things in your sample, right? Okay, but what if another chef came in when we left the room, and they dumped a bag of peas in the soup? We were totally unaware that there were peas in the soup, right? Well, if we were to very carefully take our spoon and make sure that there's a potato and a carrot and a beef and all these things that we know about in there, but we didn't even know there were peas in the soup, then we wouldn't know to make sure there's a pea in there, right? But the good news is there's a really easy way to make sure that we include everything in the soup, the stuff that we know about and the stuff that we don't know about. And that's just to randomize, stir up the soup really well so that any single soup is likely to get an even balance of the contents that are in the soup, both the things we know about as well as the things that we don't know about. And you would want to make sure that your spoon is big enough to get one of everything, but you don't have to know ahead of time what's in the soup as long as you randomize the sample. So randomness is going to turn out to be really important to get a good unbiased sample. All right, and then the third idea that's not intuitive at all is it's the size of the sample and not the percentage of the population that matters. It seems like if you had a larger population, you would have to take a bigger sample for it to be representative, but that turns out not to be the case, right? Like, well, people will say, well, okay, if I want to sample people in a high school, maybe I need to take, if there's 3,000 people in the high school, I have to have a sample of 200 students to be representative. But if I want to take a sample of the United States of America, like all the adults, since there's 350 million people, I need to take a sample of 2 million people. That's actually not true. We might still be able to get by with a sample of 200 people, even when we're sampling out of the United States. The best way to see that, I think, is with the soup analogy. Let's say that you're making your pot of soup for your family, right? But instead, you're really, really good, and so your niece hires you to make soup for the dinner. The rehearsal dinner for their wedding, right? And so there's going to be 300 people at this dinner or 200 people at this dinner. You have to make a gigantic amount of soup with the same recipe that you would in your single pot, right? So you have this huge pot of soup, right? Would you therefore need a gigantic spoon in order to taste that pot of soup? As long as you stir it up, you could get by with the same old size spoon, right? You don't have to have a gigantic ladle to taste the soup, because, as long as the spoon is big enough to fit, a potato, a piece of potato, and a piece of peas, and all the kind of things that it could be in the soup, then it's fine, right? So there is a minimum size for the sample, which we'll talk about later how to compute, right? More second semester, but that doesn't really change with the size of the population. All right. Okay. So now that we've talked about kind of some ideas, let's talk about specific sampling techniques that we use to collect samples. Okay, and this could be true whether we're talking about sampling people to give surveys to, or sampling like items off of a manufacturing line to test for accuracy or anything. Okay, the number one sampling technique is something called a simple random sample. Simple random sample, and that is used so frequently that we abbreviate it SRS. Now, here's the thing that's true about a simple random sample. The sample has to be taken from the entire population in a single step. Okay, so the entire population is available, and then you're sampling from that, right? You select some number of individuals. We usually use the letter N for the sample size for number. Using some sort of a random process, and it has to be random. It can't be people selecting, that's judgment bias. It has to be something like a random digit table, some sort of put all of the names in a hat and put them in a hat and randomize the slips of identical paper and draw them out 10 at a time or something like that. You have to use a random process, right? And here's the things that have to be true for something to qualify as a simple random sample. Every individual that's in the population has to have the same probability of being selected, and every combination of individuals has to have the same probability of selected. Okay, so for example, let's say we had all the students in a school. There were 3,100 students, and we wanted to select 50 of them, right? So we might select 50 numbers from 1 to 3,100, where the numbers 1 to 3,100 are individual numbers that have each been assigned to one of the students. So when we select all 50 out of this list of numbers, then we're randomly selecting 50 students, and that's an unbiased sample, simple random sample. All right. Second idea is something called a random sample, but without the simple part. So this is typically not used, but it sometimes happens by mistake. So a random sample is when randomization is used in some part of the population, and it's true that every individual in the population has the same probability of being selected, but it's not true that every combination of individuals can be selected. Okay, typical example of this would be this. Let's say that we had a group of 100 children, and there were 50 boys and there were 50 girls. 50 boys, 50 girls. Okay, and we wanted to select some number of boys. Actually, let me make it the whole population. 3,000. Let's say there's 3,000 people in a high school, and there's 1,500 girls and 1,500 boys, roughly. Okay, and you want to select 50 students. Okay, so one way to do that would be first flip a coin. If it's heads, then we're going to select 50 boys. If heads, then we're going to select 50 boys from the boys randomly by numbering all the boys and then using a random number generator to select 50 of the numbers and select the boys, right? On the other hand, if it's tails, when we flip the coin, we're going to select 50 girls randomly from the girls. Now, it's true that randomness was used, right? And it's also true that every individual in the population, both boys and girls, has the same probability of being selected. But what's not true is that every combination of individuals would be selected, because in this case, you're either going to get 50 boys or you're going to get 50 girls, but you're never going to get a sample that has a mixture of boys and girls, right? So while this could be called a random sample, it's not what's called a simple random sample, and this actually can produce biases. Okay. All right. The next one is called cluster sampling. Sometimes we have large populations where it would be difficult to number all the individuals for random selection, but we could divide the population into groups, which we call clusters, that are each representative of the population. And then we just randomly select a cluster or multiple clusters, and then we just choose all of the elements in that selected clusters as the sample. So here's an example. Let's say we're collecting data on the number of words per sentence in a book. Maybe it's impractical to number every single sentence and then do a simple random sample SRS out of that 10,000 list of sentences in the book, right? So instead, what we can do is first divide the book into clusters, which are the pages. So we can define a cluster to be a page, right? Basically the idea is, here's the entire book, right? And we really want to get a random sample of sentences. So we're going to take a sample of sentences from these books to analyze and find out how many words are in each sentence, right? So instead of numbering every single sentence in the entire book, what you could do is you could divide the book by pages into clusters, as long as you feel reasonably sure that every page is roughly the same as every other page. And then what you could do is use some sort of random process, like a dice roll or random number generator. So use some random process to select clusters. Like maybe I select cluster 3 and cluster 58. And that's page 3 and page 58. And then you just take all of the sentences in those two clusters and you include those as the sample, right? So for cluster sampling, you're subdividing just to make it so that you don't have to have as big of a number system to select. You still use randomness, but what you're doing is selecting clusters, and then the key idea is that all of the elements in each of the clusters form the sample. Okay, so that's called cluster sampling. Okay, and then there's another sampling where we do grouping, but it's different than this. This is called stratified random sampling. Okay, so to show you why that might be necessary, we're going to do an activity here. Typically, we would do this in the class, so I'm going to kind of describe the activity for you, and I'll show you what typically happens when we do the activity. All right, let me switch to another screen here, and I'll try to show you this activity. So this is called the river problem, and you can do this yourself, actually, but I'll have to show you what it looks like when we look at all the data from the whole class. So in the river problem, what we're doing is we're investigating a cornfield. Okay, so you're a farmer, you have a large cornfield that's further subdivided into 16 equal-sized plots. Okay, and there's a river on one side. We're interested to know how much yield, what's the yield of corn on average per plot, right? In other words, how much corn do I get per little 1/16th of the area here? Okay, and so what we could do is we could randomly pick a subset rather than measure the corn from all 16 regions. Maybe that's really time consuming and kind of a pain. So maybe we want to just take a sample of 4 plots. We're not going to base this on all of the entire land. We just want to pick 4 plots. And one way we could do this is take a random number generator and just pick 4 random numbers between 1 and 16, and then we'll choose those plots. So for example, let me share my whole screen here, and I'll show you how we can do this with a calculator. Okay, so what I'm going to do is I'm going to seed my calculator. I'm just going to type in a random, doesn't matter, just any digit, and then I'm going to store that, and then the math key, and then over here to the probability menu, and then in random. So if you store any integer into the random, what that's doing is going into the internally programmed random digit table to some random spot to start. Okay, but then I'm going to take my random integer feature, which we used back in chapter 11. So math, probability menu, random integer. And what I want to do is have between numbers 1, so I'll put 1, comma, 16. And then I would put comma 4, because I want to select 4 plots of land randomly. So I'll hit that, and it's going to tell me 4 numbers here. So on your screen, on your thing here, if you've printed this out, you can say, I'm going to pick plot number 16, plot number 1, plot number 15, and plot number 8. Those are going to be my random sample of 4 of the 16 plots. And this is a simple random sample because I selected all of them at once from the population of plots. Okay, and so let's go ahead then and compute the harvest. So when I compute the harvest, on the back of the paper that I'm going to hand out to the class or have people look at, there is a grid here that shows for all these different plots of land, how many bushels of corn came off that land, right? So I'm going to go back and look at the ones I selected, and I'll copy these numbers, right? So let's see, there were 4 here, so let me write that, 4 bushels there. Let's say I had this plot right here, so this is 153. We're 153 here. Bushels, and then these last 2 down here are 97 and 147. 97 and 147. And so what I could do is I could say, okay, to find the average, let's compute the average. We'll take each of the numbers, 4 plus 153 plus 97 plus 147. 7 plus 147, and I'll just divide that by 4 to get the average amount of corn per plot. So 4 plus 153 plus 97 plus 147. Okay, and then if I take that number and divide it by 4, I'll get, it's about 100. I'm going to round it to the nearest decimal. So I got about 100 bushels per plot, and it varied from plot to plot. Okay. And so usually what I do in the class is I have everybody do that, okay? And then I say, okay, that's a simple random sample. Now, what would it be if we did what's called a stratified random sample? So you remember how we said in cluster sampling, we would divide the population into groups, right? And then we would randomly pick groups, but then take everything in there, okay? So what we're going to do this time is I'm going to divide, but I'm going to I'm going to divide them into groups by the horizontal row. So I'm going to divide these into groups by row. Like this is a group, this is a group, this is a group, and this is a group. All right. And then the way stratified random sampling works is if I need a sample of 4, and I've got 4 groups, I'm going to take a simple random sample of 1 out of each of these groups. So I'll do an SRS of 1 out of each group, okay? So this is different than cluster sampling. In cluster sampling, right, we randomly pick a group and then we select all of the elements in the group. In stratified random sampling, we divide into groups, and these groups are now called strata instead of clusters. So this is stratum 1, stratum 2, and 3 and 4, and so on, okay? And then what you do is you take a random sample out of each of the strata to form the sample. So now I'm going to go back to my random number generator here, but this time I'm going to take random integer, and I just want a number between 1 and 4. So for this first strata here, I'm going to pick just one of those 4 randomly. And so that happened to be number 4. So I'm going to put an X here. In this first strata, we picked plot number 4. And then I'm going to run my random number generator again. I got plot number 1. So in this strata, I got plot number 1. You can do this as well. You'll get a different answer than me, which is totally normal. I got plot number 4 this time. And then I got plot number 1 this time. Okay, kind of weird that I didn't get 2 or 3, but that's fine. All right, so then I would then go back to that master list and say, well, what were the actual results? Let me write that with a different color here. So let's say I had 4 here. That was 150, 7, 148, and 5. Right? 150, 7, 148, and 5. This was the amount. And so now the average is 150 plus 7 plus 148 plus 5 over 4. Right, so 150 plus 7 plus 148 plus 5, and then I'll divide that by 4, and so that's going to give me an average of, let's say, 78 bushels per. Okay, some variation when I took the sample differently. And then we'll do it one more time, and this is also going to be a stratified random sample, but this time I want to stratify based on the column. So we're going to divide this into groups by column this time. These will be the strata, the groups. And I'm going to take an SRS out of each column. So I'll pick 1 out of each. So let me do the same thing. I'll just run that random number generator again. Okay, so that gave me 2. So in this first strata here, it's plot number 3, so that'd be this one. Let me run it again, and we'll randomly sample from this strata. We happen to get 2 that time. And then this time we got 2. And this time we got 3. All right, so we took 1 from each of the column strata. And so I'll go back to my map of the yield. And let's see, we've got, what is it, 3, 2, 2, 3. So we've got 631 for these first numbers. 631 as the bushels, and then these other ones, it's 98 and 148. 98 and 148. All right, and so now my average would be 6 plus 31 plus 98 plus 148 over 4. Okay, so that turns out to be 6 plus 31 plus 98 plus 148 divided by 4. Ends up being about 71 bushels per. Okay. So which of these is most likely to produce a sample mean that's closest to the population mean? Well, we have no idea, right? All 3 of these samples we conducted fine. They're all valid sampling techniques. We got some variation, right? We got 100 when we did the simple random sample. We happen to get 78 with the stratified by row. We got 71. How do we know which one's best? Okay, so for us to investigate that, we actually have to look at what would happen if we did this over and over and over again. So in the class, I have us do this over and over and over again, and then we make a dot plot that shows where everybody's yields came out. So I'm going to show you, this is this is a typical class, okay? If we look at what happens when we do the simple random sample, right? When we do the simple random sample, we get the average. So these are our averages. So let's add our values on here. Our values, we got 100. So yeah, our dot would be right here. Okay, and these would be the dots from other people who did, you know, random things, and they got randomly different plots of land. So there's quite a bit of variation there. Would you agree? So yes, my 100 is in here, but you know, there's a lot of variation from sample to sample. So there's a lot of variability, lots of variability from sample to sample here. Okay, and then when we did the one where we stratified by rows, we got 78. So let's put our dot on here. 78 is 70, 80, 90. 78 is about right here. So here's our dot. But again, there was a lot of variation, lots of variability from sample to sample when I included everybody else in the class, all their data, right? But then when we stratified by column, we got 71. And lo and behold, you know what I notice is that there's a lot less variability, right? So the numbers that I got each time, this number is just one of a wide variety of answers I could have gotten. This number is just one of a wide variety. But this value I got here is very close to all of the values that I got, right? So there's less variability here. And that suggests that this would be the best strategy, right? Because that means that I can trust that my number is pretty close to the numbers I would have gotten, because we all got roughly the same numbers. All right. So why did that happen? Well, if you go back to what's going on here, right? Let me go back to the original page here. Let me erase this. There's a river on this side of the plot of land, right? And so if you look at the results, right, the river is over here, right? The corn that's grown near the river, or the plots of land that are near the river, are naturally getting more water soaking through the soil to them, and the ones farthest away are the least. So if you want to have a good representation, you want to include some of the corn from each of the distances from the river. And that's why stratifying, this would be called stratifying, or stratified random sample. That's the name of this, stratified random sample. But we're going to stratify by distance from the river. Because then, if I include one out of this strata, one out of this strata, one out of this strata, and one out of this strata, I'm always going to get numbers that are roughly the same, because there's most of the variation is in this direction. So if I include some from each of the distances, that's the best method. Okay, so the river activity helps us to see why in some cases it might be better to deviate from a simple random sample. And that is if we think there's some sort of pattern in the data, like the data is getting steadily lower as we go away from the river, so we want to include some from each. Okay. All right, so let me go back to the notes here, and we'll finish up the notes now that we've done the river activity. Stratified random sample is if we suspect that there might be differences between subgroups that matter, and we want to highlight or analyze these differences, we can divide the population into groups that are different in some way, like distance from the river, or maybe gender, or maybe grade in school, or the amount of education someone had. Now those groups, instead of being called clusters, are called strata. And then we do an SRS from within each stratum to get the total number that we want. Okay, this often will be more precise, and there'll be less variability if we use a well-chosen stratified sample. Now, it's not going to work if I stratify on the wrong thing, right? Because if I stratify on columns like I did here, right? If you look at the numbers here, if you were to stratify on the columns, that's no better than just using the data as well, because if I get one from each of these columns, then I could get, I could get a bunch of small numbers, right? Or I could get a bunch of big numbers. And so that's no better, because there's no differences this way. This is the wrong way to stratify. Instead, you want to stratify based on the distance from the river. So it has to be a well-chosen stratified sample. All right. Okay, so yeah, the one thing I should note is that the first way we did this, the SRS in the river problem, it's not incorrect, right? It does not produce biased results. All three of those results, if we look at the results from the class, they're all centered at the true value. In fact, if you were to find the average of all 16, the average is 70, right? So all these are on target, right? The only difference is that by choosing stratified random sample over system, we were able to reduce the other enemy of statistics, which is variability. Okay. Okay, so let's say that there's some proposal. This is a different problem now, to double the amount of money that gets taken out of your workers' check to fund the Medicare system, which is a system that pays for some of the medical expenses of people who have retired from working. If we wanted to judge working adults in America, or we just wanted to gauge the results in America of what people thought about this proposal, and we decided, okay, maybe there's differences between the people that might respond differently here. How would we do a stratified random sample? What variable should we stratify on, right? So it would make sense to stratify on something like, say, age, right? Because we suspect that younger people who are farther away from the point in time where they would be able to use this service are going to have a different opinion of this than people who are already retired or near retirement age. So we want to stratify based on something like age to make sure that we get some older people and some younger people in the sample, right? And that's likely to be better than just an SRS of the entire population. Okay, and then there's a couple of other offshoots of those four main types of sampling. Really, the biggies are the three biggies are a simple random sample, SRS, cluster sampling, and stratified random sampling. But sometimes we have to put them together in different combinations. This is called multi-stage sampling. So you can do stratifying, clustering, and simple random samples together. Let's say, for example, that you want to calculate the number of words in a sentence in a book, right? You could first stratify the book into portions. Maybe you think that the beginning of the book is different from the middle, is different from the end. So first you would divide the book into strata, beginning, middle, and end, right? But then within each section of the book, you think, okay, really every individual page is basically identical within each one. So I'm just going to number the pages only, right? And then you do some sort of a random sample of clusters. Actually, let me do that in green. So you do some sort of a random selection of clusters. Like maybe in this strata you select this cluster and this cluster, and in this strata you select this cluster and this cluster. In this strata you select this cluster and this cluster. And then maybe we don't want to take all of the sentences on the page. We only need a few sentences. So within each of the clusters, you do an SRS. So you're actually picking like 3 sentences from within each of the clusters, which were then inside one of the 3 strata, right? It wouldn't have to be 3 every time. It could be like 5 of one, 2 of the other, and so on. But this is called multi-stage sampling, because first we did stratifying, and within each strata we did cluster sampling, and then within each cluster we also did an SRS, right? So anything like that is called multi-stage sampling. So there's another method, sometimes gets done, it's called systematic. So systematic does not use randomness, no randomness. Instead, it uses some sort of a system or a rule or an algorithm. Let's say we're doing the sentences in a book thing. So select sentences to measure in a book. Instead, instead of numbering every sentence, which is a big pain, maybe we could just start with the first sentence and then just count off sentences. And when we get, so we include sentence number 1, and then we add 100 to that. And when we get to sentence 101, we just select that sample, and then we add another 100 to get 201, and we select that SIMS. And so we're just selecting, we're not selecting SIMSes at random, we're selecting using some sort of a rule. Every 100th SIMS gets included. That can still be reasonably good. It's not a simple random sample because not all samples have equal likelihood of being selected. But we call that method systematic sampling. Okay. And then the last one, which should never be done, is something called a convenience sample. So convenience sample is just when the researchers select individuals in some way that's just convenient for them, the researchers, to do. So for example, let's say that you want to ask a survey, right? So you just go on one day at one time of day and you just ask the next 100 people who exit one grocery store what they think. Well, that's convenient for you as the researcher, but that's not going to be very representative of the population as a whole. It might be fairly representative of the population who shop at that time of day at this particular store in this particular city, but that's not going to be generalizable to very, it's almost guaranteed to produce an undercoverage bias, right? So that's a bad sampling technique. The other ones are reasonably okay. Just to emphasize the difference, let's take an example of a high school. Let's say we have freshmen, sophomores, juniors, and seniors, right? If you do a simple random sample, then that means you're gonna, maybe put slips of paper, each containing the ID of a single student for all the students in a box and randomly draw them out, or use a random number generator to select, some number of students' names. So there's a lot of different things that can happen with an RSRS. You're probably gonna get some from each class, right? But you could theoretically get just freshmen and juniors and no sophomores or seniors happen to get included, right? Or maybe you could just, it would be pretty unlikely if you took a big sample, but you could get just sophomores. All of these things can happen with a simple random sample. If you decided to do cluster sampling, then you would be saying, okay, I don't think it matters whether somebody's a freshman, sophomore, junior, or senior. They're basically all the same. And so what I'm going to do is I'm just going to divide this into clusters by class, and then I'm just going to randomly pick a class, like roll a dice, and if it comes up, number 4, it's going to be the seniors, and I'm just going to take all of the seniors. And then maybe in a different sample, it would have been all the freshmen or maybe all the sophomores. So in this case, we would never get any sample that has a mixture of grades. It would be all one grade. Randomly selected which grade, but it'd be all that grade. And actually, to qualify as cluster sampling, you'd have to take all of the seniors, all of the freshmen, all of the sophomores. Stratified random sampling would mean, okay, I think there's differences in the grades for whatever we're researching. It matters whether you're a freshman, sophomore, junior, or senior. So what you're going to do is take an SRS out of each of those strata. Those groups are now called strata to form the sample. And so that sample will be guaranteed to include some freshmen, some sophomores, some juniors, and some seniors, right? You would want to do that if you think that the class makes a difference in whatever it is that you're researching, okay? All right, so that's chapter 12. Basically, lots and lots of terminology.